I forgot to share this. I love this comic. I was going to share it either right before Thanksgiving or right after, but I could share it still here. So maybe Monday would have been better. So I hope you had a better Thanksgiving than Big Bird. I like how it's got Big Bird's legs here. Poor Big Bird. Today we'll finish up mass spec. We pretty much covered it all, but I'll finish it up. A couple things I'll add into that, and then I'll do some practice with it. Get you ready for the quiz, and then chapter 8. So as always, come to lab early if you like, and finish and turn in extraction lab this week. I know Tuesday and Thursday is tough. Well, I'm gonna get a head count and see where everybody is on that. And I extended the extractions and chromatography labs due dates. Try to get that chromatography experiment done this week if you can, but next Tuesday you can work on it too. And homework F, hopefully you've been making progress on that since we finished that a while ago. Let's do not next week, it's this week. I'll change that. This week. All right, and then the mass spec quiz. It's if you click through this GSA, and when you're clicking through it, it's best to have a piece of paper and pencil or pen or something, and be writing out the examples as you go after you've seen a couple and you kind of know what to expect to practice it. And then there's a quiz at the end, which I'll go through today's lecture. And I have some rule of 13 examples worked out from last year's honor students. So there's a bunch of rule of 13 practices you could try if you want. It's on our animation sheet, but it's on the sheet 2. If you look down at the bottom of the animation sheet, sheet 2, chapter 11. And here are answer keys to similar quizzes like your one you're going to get. So I gave 2 quizzes, mass spec quizzes last year, and then here's the keys to them. But the one that you get today and tomorrow will be different than this, but very similar. It's good to check it out. And then distillation and GCMS, the all online one, just a reminder, get that one done. Should take you about 3 hours. And end of the year, or ending out the semester lectures. So today will be a normal lecture. We'll finish mass spec, start chapter 8. And then on Monday, next week, we'll have a kind of normal lecture. I'll continue chapter 8, but I'll do a lot of examples. I'll try to present the material in a way that's like, as you're watching the lecture, you're learning it. I'm not just giving you a big list of things to go learn on your own later. I know it's the last week. And then on Wednesday, the last lecture of the year is the final exam review. So I won't present new material there, but it'll be very good to go because I'll review some of the old stuff and try to get you really prepared for that exam. And then locker checkout next Monday, Tuesday with extra credit opportunities. So if you have all of your equipment in your locker, like all the whatever on your locker check-in sheet, I'll give it back to you. Whatever the correct number of beakers, Erlenmeyer flasks, things. If you have everything just right, not extra, not less, and it's clean. So when I open the drawer to check it, it sparkles. Bling! I'll give you extra credit. So 1 point extra credit. And when you're going through your locker, you're going to be missing maybe something here and there. You're going to ask for it first before you have me like check your locker to see that everything's there. So. All right, and then clean out, if you want to get more extra credit, you can clean out a locker of someone who hasn't showed up. And like, we've got a few students who kind of just had things come up in life and they haven't showed up for the last few months or month or whatever. We'll clean their locker out for an extra credit point. And we can clean up other things in lab because sometimes I run out of extra lockers for people to clean up, but it's nice to give them a chance to get extra credit if they want to do something like that. So I can point out things around the lab to clean up. And let me know on campus if you did no Shavember. I still have not shaved. I bet some of you had fun shaving today. Let me know if you did it. Just go there and I'll give you the extra credit. You don't have to prove it. Just tell me you did it. And then final exam details. So the final exam is next Thursday in lab. You'll have 3 hours to complete it like a normal exam. And you can start early. Wednesday lab students can come at 10:45 or can come at 1 p.m. instead of the normal 2 p.m. Tuesday, Thursday, 10:45 students can come an hour early. The 2 p.m. students come an hour early. And place your cell phones at the front as usual. Come in quietly if others are taking the exam. And it'll be cumulative. All my exams are cumulative. You're probably used to that now. But it'll focus more on the most recent material. It'll have all of chapter 7 outcomes, all of the mass spec material we've gone over, and then some of chapter 8, not a lot of chapter 8. We're gonna see how much we get to. And then you'll definitely have questions related to the overall reaction mechanism and energy versus reaction coordinate diagrams of the big 4 reactions from chapter 6 and 7, the SN2, SN1, E2, E1. So practice those mechanisms. Here's some simple practice of those. And then here's honors students from this semester with some, these ones are nice because this practice has the energy versus reaction coordinate diagrams with the Hammond postulate considerations. And I really like the E2 reaction, the anti-periplanar part of it. So I'll probably give you 2 questions related to this. I'll give it to you like in a forward direction where I give you an electrophile and a base, and you have to like rotate the molecule to put the hydrogen 1 carbon away. Anti-periplanar, and then determine, oh, does that give me the Z alkene or the E alkene? So practice those. And I'll give you then the reverse reaction kind of. I won't give you the reactant, the electrophile, and I'll say what electrophile would give just this E or just this Z alkene. And so practice those. I have examples of both in the lecture Jamboards and in the as part of the chapter 7 homework, I have you do a worksheet on that. And then I'll give you a question where I'll give you an electrophile and a nucleophile / base, and you have to figure out what's the major reaction pathway, what will happen the most, SN2, SN1, E1, E2. And then whichever one happens the most, you'll say, oh, this should be the major product of that. And mass spec, I'll ask you some cleavages. Is someone have a question, or maybe I needed to learn how to mute all? Remote control.
Oh, sorry, I'm just talking to my cat. Ignore me.
Okay. And then mass spec, expect the cleavages, practice the alpha cleavage and the McLafferty rearrangement. And rule of 13 calculation on a multiple spectrum problem. So instead of being given a molecular formula, you have to generate possible molecular formulas with the rule of 13 calculation. And then you'll get help from the other spectra, like, oh, on the carbon, I have a carbonyl in the IR, so I need to add an oxygen into my formula, things like that. And then chapter 8 material. So we'll only cover about a third of it, and we'll pick up from there in 12B. And I'm hoping to get to chapter 8 outcomes 1 through 15. And that sounds like a lot, but there's a lot of really short ones, which are like basic stuff, like general chem stuff. But I'll let you know if I get less material, what we're going to actually have on the exam after today's lecture. And older material, I like to put on exams, things like you haven't seen in a little bit, maybe like a sigma pi bonding diagram. That'd be good to practice the one from the exam or from a homework or something. Chair conformations of cyclohexanes, draw some pairs, cyclohexane chairs, get some practice. Newmans of alkanes and cycloalkanes, practice a couple of those. And then Fisher projections, that's not so old, we just had on the last exam, but practice that a little bit. And the absolute configurations, we've been doing that all along, the RNS, but practice a little of that. And then other old stuff relating to stereoisomers, not really that old, we just had it on the last exam, the enantiomer, diastereomer stuff. And then the radical halogenations of alkanes, we've done a lot of that this semester. Maybe draw out the curved arrow mechanism again. It's probably been a little while since you did the initiation, propagation 1, propagation 2, terminations and all that. And then energy versus reaction coordinate diagram. And I'm listing a lot here that I could put on the exam, and I won't be able to do all of this because I don't want to make the exam 6 hours, but this is the type of things you should review so you're ready for whatever comes. Any questions about that? Oh, and then I got a question about when you're checking out of your lockers, when you might find you have extra glassware, I'll have you bring that up front. And then when people who are missing glassware, we'll try to get the extra glassware to put in their locker. And then if there's not any of the, the extras up front, then we'll get it from the stocker. Okay. All right, not any other questions. I'll start the lecture. I'm going to start off by reviewing real quick this mass spec basic concepts here. I'll go to slide 11. I'm in the mass spec material to master. Let's just do a quick review with this. I'll try to help everybody get through all their experiments too, like the chromatography lab. We can talk more about that in lab. All right, so here we go. Oh, this is slide 11. Actually, yeah, I want to back it up. Here we go. So in a mass spectrometer, you have a molecule. It gets injected into the mass spectrometer. An electron beam can come through and hit it, knock off an electron. It could knock off a lone pair electron, a sigma bonding, or a pi bonding, but we don't have pi bonding. And then I think it most often takes off a lone pair electrons. And then we can calculate our molecular formula for this molecular ion and use its most abundant isotopes to get its mass to charge ratio. And it's a high energy thing. It's got a radical and a cation. So it can cleave, it can do an alpha cleavage like that and make a number of my carbons, make sure I didn't lose any. It can make this charged particle with that formula, which then would weigh 59 mass to charge ratio because I'm using its most abundant isotopes. And this one has no charge, so it won't be detected. And then we can get another alpha cleavage on the other side. Drop off this methyl. This losing a methyl from a molecule in a alpha cleavage or any kind of other rearrangement or anything, it's pretty common to lose a methyl. And a methyl is carbon 12 plus 3 hydrogens. So what should a methyl weigh? A methyl should weigh 15. It does weigh 15. So people who use mass spec a lot, they'll often look at the mass spectrum and look for a -15 signal, like whatever the molecular ion is. If they see something -15, they're like, oh, that molecule has a methyl in it. It tells them right away, I got a methyl. It's kind of a nice little thing to notice. Okay, and I can number my carbons so I didn't forget any. And then, yeah, I got my formula. And then these particles get shot towards the magnetic field and their path is bent according to their mass and their charge, but they're all +1, so it's just mass. So the most massive molecular ion hits at 88. The medium massed, the one that just lost 15, 88 minus 15, 73, hits in there, and then the other one bends the most. And the non-charged particles not detected. Here's the mass spectrum. This one, it was the molecular ion peak was cut off for some reason, but it should be there. And then maybe it was just super small. Maybe it rarely survives in almost all fragments. But then we can see the other ones. We can see this guy here, 59. That's the base peak. That's what happens most often. This cleavage with the ethyl radical and protonated acetone kind of thing. And then here we got this one. That's it. 74. It looks good. Or 73, sorry. And you'll notice too, what's this one, right? I got the 59, the base peak. That's this guy. What do you think at 60 is? What's causing this signal at 60? Yeah, that's an isotope peak of this fragment. So this fragment could have a carbon 13 here or there. And then everything else, most abundant isotopes, it would show up at 60, one heavier, or it could have a deuterium here or there, and that would make it one heavier. So that's an isotope peak of this fragmented piece. And you can see for the other one too, like this one, there's an isotope peak right there. Okay, so that's a quick little review. Now let me point out a couple things I haven't mentioned yet. Some I've mentioned and some I haven't. Let's look at hetero atom equivalence. So when I say heteroatom, when you say heteroatom in organic chemistry, it refers to atoms other than hydrogen or carbon. Because organic molecules are mostly made up of carbon and hydrogen atoms. So yeah, chemists have decided to call other atoms heteroatoms. So heteroatoms, for example, would be most common oxygen, nitrogen, bromine, just other things, you know, that we see in organic molecules. Okay, so what am I talking about with this equivalence? I'm trying to figure out now, what is the equivalent mass of, say, an oxygen atom? We already did that one. So what is the equivalent number of carbons and hydrogens for oxygen? Oxygen 16, its most abundant isotope. That's right. Oxygen is C. Oxygen 16 is equivalent to most abundant isotope of oxygen 16. Carbon and 4 hydrogens, because it's carbon 12, right? And H1, so 12 plus 4, 16. I'll make it different colors. 16. All right, so if we got that, then we can add on nitrogen. What's with nitrogen? Nitrogen's most abundant isotope is nitrogen 14. And what would its equivalent number of carbons and hydrogens be? Oh. CH2. That's right. So if I have a formula that I first derived, that rule of 13 derivation, and it only has carbons and hydrogens, I can add an oxygen or nitrogen by subtracting out, for oxygen, 1 oxygen, I'd subtract out a carbon and 4 hydrogens. For a nitrogen, carbon and 2 hydrogens. And there's something else special about the nitrogen. And I'll help you remember it by saying, that's odd. I don't know why I like to say it that way, but so when you have an odd number of nitrogens in a molecular formula, that means its molecular ion will be an odd number. That's odd. Molecular ion. This is a really nice way to notice if you have a real strong hint if you have a nitrogen in a molecule. So for instance, let's look at an example. Let's look at a molecule like a real simple one, CH3 NH2, methylamine. So this formula is CH5N, right? What's its mass? 12 plus 5 plus 14 for the nitrogen. That adds up to 2631 mass to charge. That's odd. So if you have a molecule that's got a molecular ion that's an odd number, it should make you think, oh, it has an odd number of nitrogens. And for the examples I'm going to give you, just assume it's one nitrogen. Because, yeah, to give you 3 nitrogens, that's kind of pretty tough. I would let you know if I wanted to do something like that. I'd make it obvious. Let's look real quick at some STBS. Let's see if we can find some. That's odd. Let's look up this first one. CH5N. Methylamine. Oh, it doesn't have the mass spec, of course. Let's go ethylamine. CH2, HW3, 4, 5, 6, 7. There it is. Yes, ethylamine, we got it. So when you look at ethylamine, its molecular ion is 45. That's odd. That makes you think it has an odd number. It has an odd number of nitrogen, so it's right there. That's 45. And there's an isotope peak. I don't know what this one is at 55, 56. I'm not sure what's going on with this. This is an interesting one. It's got a lot of extra. Maybe that's just noise. But yep. Yeah, so whenever you see an odd molecular ion, you think that's odd. And we'll do some examples of it and we'll work it out. Okay, and then the next one, it's not a heteroatom, kind of doesn't fall into this category in a way, but it's the same idea. If I have, say, a molecular formula initially that has like just way too many carbons or way too many hydrogens, I can use this comparison. I can use this equivalence. a carbon 12 equals how many hydrogens? Twelve hydrogens. So I can substitute 12 hydrogens for a carbon 12 or a carbon 12 for 12 hydrogens. Sometimes you have to like kind of massage your initial formula you get from the rule of 13. Okay, so those are for like our correcting our molecular formula. Another one is another interesting molecule is bromine. So you know carbon 12 and carbon 13 are the most abundant isotopes, and it's like 98% carbon 12, 1.2% carbon 13, and then hydrogen 1H2, it's like 99.99% this one, and like 0.0, I'm not even sure the number, approximately those. And then oxygen, it's like almost all, it's about 100% oxygen 16, and the nitrogen 14, it's about 100% nitrogen 14, right? So it's almost all just one isotope for these atoms. Bromine, though, bucks the trend. Bromine's most abundant isotope is bromine 79. That's its most abundant isotope, but it has a whole lot of bromine 81, too heavier. It's about 51% bromine 79 and about 49% bromine 81. So it's almost an equal mix of those two isomers. Those not isomers, those isotopes. So let's look at some of this, see how this looks. Slide 4 and 5 I said to look at next. Let's see. Oh yeah, here's some calculations first. Let's do that. Yeah. I'll do some workout examples of this too, but I'll show you. So if I get a molecular ion, say I give you a mass spec and it has a molecular ion with a mass of 61 mass to charge ratio, what do you think? That's odd. It's an odd number, right? 61. And so if it's odd, it suggests it has a nitrogen. It definitely doesn't have a bromine because the most abundant isotope of bromine is 79, and it's got less than it. But let's go back to the nitrogen. But that's odd. So normally you'll have an odd number of nitrogens. It'll be one nitrogen because we're first year organic chemists. I won't give you two crazy ones. And so we do a rule of 13 calculation. With rule of 13 calculation comes from the fact that one carbon and one hydrogen equals 13. And then we'll add in the nitrogen afterwards. So let's do it. So I got my 16 divided by 13, going old school here. And if I multiply it at 13 by 4, it's 12. Carry the 1, 5. I subtract and I get a remainder of 9. So I've got 4 CH units and 9 remaining, which I'm going to call just hydrogens initially. And then what I do is I double check it. Always double check. Do the discount double check. I like this. I like commercials. I like the one, it's old now. Does anybody know the Aaron Rodgers, the quarterback for the Green Bay Packers, his discount double check commercial? Huh? So, so you got to watch, you got to make sure you always do your discount double check. Make sure you got this right. So I could easily make this calculation, this long division wrong, but if I double check it, chances of making an error a lot less. If I made one little simple error in calculation here, it could take me like 10, 15, 20 minutes on the exam trying to figure out why I can't get this structure because I have made an error here. So it's best to double check. So what I do is I double checked it by, I take 13 times 4, which is, let me do it on a piece of paper. 13 times 4 is 52, and then I add the extra 9. Yep, that's 61. So I double checked it. This is correct. And what kind of formula does this mean? This means I have 4 carbons plus 4 hydrogens and then another 9 hydrogens, so 13. So, and then I'm going to double check this formula because this formula, this first formula, it needs to add up to 61 as well. So let's do that. 4 times 12 is 48 plus 13, 61. That does double check. Okay, so, but this formula, oh, before I even do this too, this is my initial formula, and this one is ridiculous. One way you can tell it's ridiculous is to calculate degrees of unsaturation. So the calculate degrees of unsaturation for that one, it's 4 carbons plus 1 minus 13 hydrogens over 2. Wait a minute, 13 divided by 2, that's 6.5, that's a fraction, has a fraction. So that formula you can't have half a pi bond or half a ring. So that doesn't work. This formula doesn't work. But what we're going to do is we're going to subtract out a CH2 because that weighs 14 and add a nitrogen which weighs 14. And we get this formula, C3H11N. Now this formula, it should have a reasonable, it should have a degrees of unsaturation. That's not a fraction. But let's double check first. Just this should still add up to 61. Let me do it over here. So 3 times 12 is 36 plus 11 hydrogens, 47 and 14 nitrogens. Yep, 61. This looks good. And now that's a lot of hydrogens. 11 hydrogens for just 3 carbons. This formula still might be like just impossible. The way we'll check is with the degrees of unsaturation calculation. So I'll do my degrees of unsaturation. Carbon plus 1 minus hydrogens plus halogens minus nitrogens all over 2. So I have a nitrogen in this one, no halogens though. So it's going to be 3 carbons plus 1 minus 11 hydrogens, 0 halogens, 0 bromines, iodides, chlorines, minus a nitrogen all over 2. And now this formula will be 4 minus 10 over 2. I'm doing it really slow. I don't want to make an error in my calculation. And I get 4 minus 5 minus 1. Oh, wait, that can't happen. You can't have a negative degree of unsaturation. That means, yeah, it means you have to break the octet rule, I think, to get that extra hydrogens on the carbons. So this formula is a junk formula. It didn't work out. We're just doing this computer mathy stuff and it didn't work, but we're humans. We can figure it out and we can fix it. So the problem with this formula, too many hydrogens, huh? How can I get rid of some hydrogens and still have a formula that weighs 61? I don't have enough carbons for that many hydrogens. One way you can do with this is you could add an oxygen. I saw some people say add a nitrogen. You could try adding another nitrogen, but you'd have to add 2 more nitrogens because you need an odd number of nitrogen. So I'm going to add an oxygen. Oxygen weighs 16, so I'm going to subtract CH4 and get C2H7NO. And for this one, let's double check it. Does it have the right mass? So C2, that's 12 times 2, 24. Plus 7 hydrogens plus 14 plus 16. So I get 21 there, 40, 50, 61. This double checks. And let's check the degrees of unsaturation now on the next slide. It's going to be 2 carbons plus 1 minus 7 hydrogens plus 0 halogens minus a nitrogen all over 2. 3 minus 6 over 2, 3 minus 3, 0 degrees unsaturation. That's possible. We can have that. And I'll double check my math. It is 2 plus 1 minus 7, 0, 2, 3. Boom, we got it. Yep. So I can start drawing up some possible examples. I know I need 2 carbons and a nitrogen and an oxygen. So I can start off by like, okay, I'm going to draw 2 carbons and I'll add an NH2. Another and an oxygen, and I make sure I don't add any double bonds. And does this work? Let's see. It needs to have 7 hydrogens. 1, 2, 3, 4, 5, 6, 7. Yeah, that works. Or I can go, I'm gonna put an oxygen in the middle of 2 carbons, like kind of looking like an ether initially, and add an NH2 off of there. And yeah, that should be 0 degrees of unsaturation, and all my carbons and oxygens are correct. So I should have the right hydrogens. Let's check. 1, 2, 3, 4, 5, 6, 7. Looks good. Or here's another one. Put the nitrogen in the middle. 1, 2, and then, 1, 4, 5, 6, 7. Yeah. Or I could try adding another oxygen too. So I can subtract another CH4, add an oxygen, because oxygen weighs 16, 12, plus 4 is 16. And I get CH3NO2. Okay, and then double check this. Does this add up to 61 still? Let's see, 12 plus 3 is 15, plus 14 for nitrogen is 29, plus 2 oxygens would be 32. Yep, 61, looks good. Now my degrees of unsaturation are 1 plus 1 minus the hydrogens 3, no halogens, and nitrogen divided by 2. Notice oxygen is not in the degrees of unsaturation formula. So it's 2 minus 2 over 2, 2 minus 1. Oh, we got a degree of unsaturation. Does that seem reasonable? Yeah, that seems reasonable. So, and I double check my calculation, looks good. And now 1 degree is possible. Let's draw. Oh, this could be nitromethane. This is a common organic solvent, actually. Has resonance. Oh, what happened to that guy? He moved. Nitromethane. We'll see a lot of nitro groups later. Let me fix mine. Beep, beep, beep. Yeah, he got moved over somehow. Oh, I should probably go down 1, 2. Perfect. So yeah, nitromethane will work. And nitromethane does have a single pi bond, so it has the correct degrees of unsaturation. The nitrogen has a positive formal charge always on nitro groups, and then oxygen shares its negative charge. So it all adds up to 0 like it should, because it's 0 here. And it's got 1 carbon, 3 hydrogens, 2 nitrogens. Oh, looks good. Here's another example of this formula. It has 1 pi bond and looks good. And this is a very reactive molecule. It's called carbamic acid. So it's carbamic acid because it likes to go bam. If you heat it up above minus 23 degrees Celsius, it explodes. Bam. So not very stable molecule. It explodes to carbon dioxide and ammonia. But if you have it in like a dry ice acetone bath, which is minus 78 degrees Celsius, you can have it not explode on you, but let it warm up. Boom. It's gone. Yep. All right. So we're getting good at adding nitrogens into formulas. Let me see what's on my list next. The bromine stuff on slides 6 and 7. Oh, that's right, in line with what we're doing. So here we go. If we have a molecular ion of 108 and it has an isotope peak that's slightly shorter at 110, that tells you, oh, it looks like we got a bromine, because bromine 79 isotope is about 51% abundant, and bromine 81, its other isotope, is about 49% abundant. So that gives you the 110. And so what I do before I do the rule of 13 calculation, I just take the bromine out of the number. So I'm going to take my molecular ions 108. I subtract the bromine mass right away. And then I do a rule of 13 on what's left. And I double check all my calculations as I'm going through. So when I do this one, I get a 2 remainder of 3, which means 2 carbons, 2 hydrogens plus 3 more. And then I add on my bromine because I subtracted it there, right? And I double check this formula. Does it weigh 108? Let's see, 24 and 5 is 29 plus 79. Yeah, 8. Yeah, looks good. And this is an even number. It's not odd. I don't expect nitrogens in it. So I do my degrees of unsaturation and I get zero degrees of unsaturation. Seems reasonable to me. And so now if I want, I can add in an oxygen. Why not? See if that works. I get CH bro, CH BRO, CH bro. Double check it, it works. This does weigh 108 as well. And then degrees of unsaturation, 1 degree unsaturation. I think we can pull that off. So let's see, let's drop some molecules for these. Oh, I didn't animate that yet. Oh yeah, no, I know I need to do. Sorry. I made changes to this right before lecture today. I need to delete this guy. Yeah, boom. Okay. So my first formula with 0 degrees on saturation, this is the only thing I can draw that makes sense to me, because bromines are normally just on the outside of a molecule like hydrogens. And so when I add it to the outside of the two carbons, 0 degrees unsaturation, that's it. And I look up the mass spectrum, and here it is. And look at that, isn't that great? Our most abundant isotope, bromine, with the bromine 79 and carbon 12s and hydrogen 1s, this molecular ion, and then here's an isotope peak. It's the molecular ion plus 2 because it's 79 to 81. There's about 51% bromine 79 and that causes the slightly taller peak at 108. And then there's about 49% bromine 81. So that causes this slightly shorter peak, 49%, at a 110. Pretty cool, huh? So when you see a mass spectrum, I like to give bromines on mass spectrum. So if you see one on the final exam and it's got like a doublet looking signal for the molecular ion, with the lighter one a little taller and they're 2 apart, then you should think, oh, there's a bromine in this molecule. The it's the tail of a bromine in a molecule. What about this little guy right here? Say this is 108. What about 109, that little 109? What can cause that? There isn't really much bromine 80 isotope because bromine 79 and 81 make up about 100% about. But the rest of the molecule, you could have like a carbon 13 here or a carbon 13 there, or a hydrogen deuterium here or deuterium. So if you have either one carbon 13 or one deuterium, then that would make that one slightly heavier at 109. All right, and then our second formula was CHBRO. CHBRO. It has 1 degree of unsaturation. This is the only thing I can draw up that seems reasonable. And this doesn't even look very stable. This looks like something that would this would kill you if you breathed it, I'm thinking. It looks too strong of an electrophile. And again, for this one, I looked it up on SDBS and it didn't have it because I think it's just that molecule is too high in energy, I think, to get a mass spec of. And as you see in this one, bromine and halogens tend to just add to the atoms, add to molecules as single bonds on the outside, right? So you can interchange a hydrogen and a bromine, and hopefully that makes sense to you in terms of our degrees of unsaturation formula, because remember in that formula, we have hydrogens plus halogens, so they're treated the same. It's kind of nice to see that, right? Let's see here to go to, yeah, skip that. Slide 21 to 24. Okay, before I do that, I'm going to write a little something on the Jamboard. So you know how for our degrees of unsaturation formula, it's carbons plus halogens minus hydrogens, or carbon plus 1 plus halogen minus nitrogen all over 2, right? Fluorine, chlorine, bromine, iodide, pretty much, right? Okay, so if I look at a molecule and I go, oh yeah, I've got this molecule versus the bromide. You see how the bromines and the hydrogens are pretty much the same. You're just like replacing a hydrogen for a bromine. And that's why they both get treated the same in the formula. Does that make sense? I'm kind of just giving you not like a proof of this formula, but just like an intuition about it. So, and then the other thing is, what if I compare like this versus the amine? So this amine still has 1 hydrogen here, and the propane has 2 hydrogens. So what happened in this case is, see how I replaced 1 hydrogen with a nitrogen and 2 hydrogens, and thus I added an extra hydrogen with that. So my formula has to lose a hydrogen, has to lose a 1 for the nitrogen, right? Kind of nice, right? And then finally, if I have like, say, this versus, if I put an oxygen in this molecule, they're both C3H678, C3H8O. Do you notice how they both have 0 degrees of unsaturation? So the oxygen didn't matter. And it's not in the formula. Kind of nice, right? This formula you've been using for a little while now. Can I explain it a little more? I don't know if I said that before. So the oxygen, I think of it as sort of like it just inserts itself in the middle of a bond. It's like an extension cord, so it doesn't add or take away or affect the degrees of unsaturation. Let's get back to this. Here's another example with the bromine. I'm going to do one more in this animation, and then I'm going to do the sample quiz for you. So here we go. Here's 1-methyl 3, no, 1-bromo 3-methylbutane. 1-bromo 3-methylbutane. There we go. Here's its mass spectrum. And a lot of times you'll see this with bromine. Its molecular ion and its isotope peak are pretty small, meaning that the original molecular ion breaks down really a lot. Like it's almost always breaks down. When it's not obvious what your molecular ion is, like in this example, if I were to give you this on a quiz or an exam or something, I'll let you know, oh, that one's the molecular ion because it's not super obvious, but there it is. So it's made of the most abundant isotopes. So here's bromine 79. That's the most abundant isotope of bromine. And so this formula is C5H11Br. And so the molecular ion mass is 150. And there it is, right there, that little guy. And see how it's slightly taller than the 152, 2 over. So that 2 over, yeah, it fragments a lot. So bromine, when you have the molecule with bromine 81, it's a little less abundant, 49% abundant. So it's going to be 2 heavier, it's right there. And then there's also like a little tiny peak right here and a little tiny peak right there. Let's look at those. So sometimes you can have a bromine 79, but then in all the carbons are carbon 12, but one's 13. So it'll be 1 heavier than the molecular ion at 150. It'll be 151, that little one right there. And then you could also have bromine 81, an isotope. What? Oh, no, I'm sorry. This is just another, instead of a carbon 13, we have a deuterium. So H2 deuterium, it'll also show up at that position there. Or, but you most likely will have carbon 13 over hydrogen deuterium H2 because it's 0.01% abundant, the deuterium, and the carbon 13 is 1%, about 1%. All right, and now we could have a molecule with 2 isotopes on it. The bromine 81, which is like 49% of the chance you have that, and then 1% of the chance you have a carbon 13 somewhere. That'll give you that little guy at 153. But it could also be caused by, if you have, instead of a carbon 13, you have all carbon 12s, but 1 deuterium, and it's right there. It's nice, right? Able to label all these nuances. So we're able to label all 4 here. And let's label some more too. So this is a carbon with a bromine. This is the alpha carbon. We can do an alpha cleavage, where the radical electron comes down, and then imagine 2 electrons in here, one going to make a double bond to the bromine and the other one breaking off a primary radical. Now we have a primary radical, no charge, won't be detected. But we have this bromine cation, that'll be detected, CH2Br, so that'll weigh 12 plus 2 is 14 plus 79, that'll equal 93. So that's a signal right there. It's a fragment, 93. And if it has a bromine 81, instead of 79 here, if it has an 81, it's the one right there. Pretty nice, huh? The isotope peak of the fragment. And then let's try some more. This is an interesting one. This isn't one that we've learned, but this one, if you break up the bond, not between the alpha and beta carbon, but the beta and gamma carbon, you break that, you can make this bromonium, we call it, and then the radical won't be detected. And this bromonium, we'll be talking about it a lot next year. Bromonium. It has a molecular ion of, not a molecular ion, it has a mass charge ratio of 107 when it's bromine 79, the most abundant isotope. So there it is. That's a nice looking peak. Then 109 when it's the bromine 81 right there. And so bro, this here is bromonium. These brodaceous cations are actually pretty common. So we'll see those next year, next semester, next year. Okay, and now 43 is the base peak. That's the tallest one. That's what happens the most. So let's see, what could that be? That could be, if I do a rule of 13 on that one, C3H7. So it could be just this part, these 3 carbons with the 3 hydrogens on each methyl and then 1 hydrogen there. So this one's kind of crazy. How could we get that right there? It seems that's probably what it is, 43. So it's kind of like a puzzle, try to figure out a mechanism for it. So this is my guess. Maybe it has like a hinge here, and that swings away to make the secondary carbocation and a bromine atom. So you get a secondary carbocation, ethene, which is not detected, bromine atom is not detected. So we did break 2 bonds, but we got rid of the plus charge on the bromine, but the bromine, yeah, got rid of the plus charge on the bromine. But you made 3 particles. So in terms of entropy, it seems favorable because if you go from 1 thing to 3, there's more disorder. So that would make 43. So I don't know if this is it. I don't know if any of my mechanisms are right. They're all just our best guesses, but this seems like a reasonable one to me. This isn't something I'm going to ask you to do on the exam, just an interest. All right, so sample quiz. So I said to you, this sample quiz is the one you're getting today and tomorrow. So let's go ahead and just make an answer key for it. Let's do it. All right, first off, I'm asking about a molecule with a molecular ion of 71. That's odd. 71's odd, right? So what should we do about that 71? What's that telling us? If it's an odd molecular ion, it's probably got an odd number of nitrogens. And odd number of nitrogens, we're going to usually just go with N, with 1. That's odd. So with nitrogen, I like to do rule of 13 on the full 71 and then add the nitrogen later, like I do with oxygen. But with bromine, since bromine 79 is so big, I usually subtract the bromine out at the beginning. You could subtract the nitrogen 14 from 71 right now, but I'm going to do it the way I usually do it. 13, I'm going to see how many CHs are in this. So, oh, and if you want to do it on your calculator instead of the long division or just get the answer quicker, you can go 71 divided by 13. I get 5.4615, whatever. So I know it's going to be 5. So it's going to be 15565, right? 15, 5, 6. So that's going to be 6, and that's going to go 6. So it's just a remainder of 6. But on my calculator, I've got 5.4615, whatever. So if I subtract 5 from that and then times it by 13, I'll get the remainder 6 as well. If you want to learn how to do that, just ask me. And I got to double check this. I'm going to double check every time. 13 times 5 is 15, 5, 65 plus the 6 remainder. Yep, 71. Okay, so first formula from that would be C5H5 plus the extra 6, 11. And it's already looking weird because it's got an odd number of hydrogens. If I were to not know that that's odd, it has a nitrogen. Let's say I tried to do the degrees of unsaturation for this one. It would be 11 over 2. And that would be 6 minus 5.5. What? It's got a half a degree of unsaturation? Nonsense. So that's not good. That should clue you to like, oh yeah, wait, I can subtract a CH2 that weighs 14 and add a nitrogen. So I get C4H9N. All right, now it's gonna work out. I think this is a good one. Let me double check it though. Discount, double check. Carbon times 4 is 44, 48 plus 9 nitrogens. That's 17, 57, 57 and 14. 71 looks good. Did my discount, double check. Now degrees of unsaturation. I think this is a formula that's going to work. Let's double check though. It's going to be 4 plus 1 minus hydrogens 9 plus 0 hydrogens minus 1 nitrogen all over 2. 5 minus 8 over 2. Good. This is not going to be a fraction. 5 minus 4. It's got 1 degree of unsaturation. I like it. That works. So my formula for this answer could be C4H9N, and it has 1 degree of unsaturation. And a possible structure, there's lots I can go. That works, huh? C4, got 4 carbons, 1, 2, 3, 4 carbons, and it's got 1 degree of unsaturation in the ring. So it should have still 9 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks good. Let me try another one. I'll put like an alkene in a ring, maybe. 1, 2, 3, 4, NH2. Does that work? 1, 2, 3, 4. Yes. And does it have the correct number of hydrogens? 2, 3, 4, 5, 6, 7, 8, 9. Looks good. So there's more, many more you can draw. Let's do another formula though. How can I generate another formula? It looks like I've got some really nice, I got a nice one already. Yeah, I can add an oxygen. So I could take my C4H9N and I could subtract how many carbons and hydrogens to add an oxygen? CH what? So Carson's asking, did I have to give 2 examples on, it's whatever my instructions say. Draw possible structures. So I guess you could do 1 each, that's still structures. Okay, C3H5, no. Okay, did I do that right? This should still add up to 71. Let me see. So 3 times 12 is 36 plus 5, that's 41 plus nitrogen, 55 plus 16, 71, looking good. I think this is going to be our second formula, as long as it's got a decent degrees of unsaturation. So let's check. Degrees of unsaturation is 3 plus 1 minus hydrogens, 5 plus 0 halogens minus 1 nitrogen all over 2. 4 minus 4 over 2. 4 minus 2. 2 degrees of unsaturation. I think we can do that, no problem. So I'm going to go with this formula. C3H5, no. It has 2 degrees of unsaturation. And let's go. I can make an alkyne, maybe. And that'll just add on then 1 more carbon and a nitrogen and an oxygen. So maybe I'd go, this one's a little weird, but it'll work. let's see. I got 2 degrees of unsaturation there. And then I got 1 carbon, 2 carbons, 3 carbons. We're good. 1 hydrogen, 2, 3, 4, 5 hydrogens. This looks good. Let's try something a little more reasonable. I like an amide would be good. What about that one? I've got an oxygen and nitrogen. I got 3 carbons, 1, 2, 3. So I should have my 5 hydrogens. 1, 2, 3, 4, 5. It looks good. And maybe I'll go like this. I'll put the nitrogen here and put a methyl off of it. Oh wait, that doesn't work. I don't have enough degrees in saturation. Never mind. But yeah, there we go. Those look pretty good. There are more you can draw. Okay. We got that question number 1 down. Oh, I don't know why. I got like a line right through this guy here. Sorry about that. I don't know how to just erase that, but that's okay. Okay, now there's more questions though. Mass spectroscopy quiz. All right, so here we go. We got 3 heptanones given. Draw the alpha cleavage and McLafferty. So let's just figure out what the formula is for this one first. Let's go. It's called 3-heptanone. Sounds like 7 carbons, right? 1, 2, 3, 4, 5, 6, 7. There we go. 3-heptanone. Its formula is C7H14O. I know it's on. I did the H's quick because it's 1 degree of unsaturation, and that means it's got double the number of hydrogens as carbons. So there we go. And now degrees of I don't have to do degrees. Let's do the mass of this. So the carbons, it's 7 times 12, 77, 84. Hydrogens, it's 14 times 1. Oxygens, we got 1 times 16. 14, 8, 9, 10, 11, 111 mass to charge units. That's the molecular ion, right? So when this down here, I'll draw the molecular ion. It's going to lose an electron, and most likely it's going to lose it from one of these lone electrons. There we go. We lost it. And then this should weigh 114. Do we see a 114? There it is. That's the molecular ion. And then there's the isotope peak. It's likely like carbon 13 right there, right? Okay, but let's get back to our original question here, the fragmentations. So for the alpha cleavage, there's going to be 2 of them, huh? We can have an alpha cleavage to the left where there's 2 electrons in this bond between the carbonyl carbon and the alpha carbon. One of them can reach out and make that triple bond with the oxygen. So we get that radical, and then the oxygen's got triple bond plus charge, and it's still got 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5. Yep. Let me number these. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. There we go. And the formula for this is C 1, 2, 3, 4, 5. C5H 2, 4, 6, 7, 8, 9. Oh, let me double check. 2, 4, 6, 7, 8, 9. Oxygen. Yep. And what is this way? This way is 69, because it's 60 for 12 times 5 plus 9 plus 16. 85 mass to charge. So let's see, do we see an 85? Yes, we do. I see 75, 80, oh wait, no, 75, 80, 85 right there. So that's that one. And then we have the other cleavage, alpha cleavage. I don't know if I asked you for all of them. Draw all alpha cleavages. Oh yeah, I'm not having you mess around on this one. So again, meet me halfway. There we go, looking good. And the formula for this one will be C 1, 2, 3, H 1, 2, 3, 4, 5, O, and that weighs what? It's 36 plus 5, 41 and plus 16, 57 mass to charge. Yeah. But the Heinz 57 fragment here. Let me double check my math. 3 times 3, 3 times 12 is 36, and 5 is 41, 51, 6. Yep. All right, so where's that one showing up? Ooh, is that the base peak? Oh no, accidentally did something. Let me rewind that. Does that look better? Yeah. Okay, there we go. Do I see that one in here? Oh, shoot. Almost dropped the iPad. Do I see that one? 50, 55, 50, 55, 56. Yep, that's the mass peak. Nice. I said mass peak, I meant base peak. Base peak, good. Okay, lastly, so I asked, let me double check. Remember, as this, to be good test takers, we try to answer the question, then we read it to make sure we did. Draw all alpha cleavages. Oh, and McLafferty. I've not drawn a McLafferty yet. Oh, I have you label. I said to label the isotope peak and draw a representative. I didn't draw a representative of that yet. So the isotope peak will be something like this. Let's say like a carbon 13 right here. There we go. All right, so all I have left now is McLafferty. So let's do this McLafferty, finish this off strong. So this molecule, if I count around the original one from the oxygen, 1, 2, 3, 4, 5, it's not far enough on the left side. But if I count from the other side, from this side, let's go 1, 2, 3, 4, 5, I can draw a hydrogen off of here, and that could be my 6-membered ring. Good. So let me redraw this molecule in the way that it'll react in a McLafferty. And I'll number it. I got the 1, 2, 3, 4, 5, 6. But I can't remember. I still have another methyl off of 5. So let me number those, maybe the green ones. So this is 1, 2, 3, 4, 5, 6, 7. So yeah. All right, we're ready to go. Oh my goodness, I hate that. There we go. Let's zoom in a little bit. Give me some room. Okay, so imagine you have a hinge on the oxygen, and this pi bond swings out and deprotonates that hydrogen. Then you have another hinge here. And this sigma bond swings down to make a pi bond. Another hinge here at 4. And this bond swings down there. Oh my goodness. I really wish that didn't happen. Here we go. Let's draw the products of this one. I think I got to shrink this other guy a little bit. Give me some more room. No. Curse you. Okay, never mind. I'll make it happen here. Notice on this McLafferty, the oxygen with the alcohol, the hydrogen there, it starts off with 3 lone electrons and it ends off with 3 lone electrons. So it's the thing with the plus charge. All right, there we go. And maybe I'll use the green numbers to make sure. 1, 2, 3, 4, 5, 6, 7. Looking good. The formula for this fragment is C 1, 2, 3, 4, C4, H 3, 4, 5, 6, 7, 8, H8O. Let me double check that. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. 1, 2, 3, 4. Yep. This looks good. And the mass of that then would be we're out of room. I'm going to do it up here. $12 times 4 is 48 plus 8 hydrogens. That's 56. And then 56 plus 16. 1, 2, 72. Do we have some at 72? We sure do. Look at that. It's a nice one. 72. Sim 3, Sim 4, Sim 5. Yeah, there it is. So our McLafferty rearrangement product is right here. Some nice ones, huh? Okay. I think I answered everything. Let me practice good test taking techniques. So did I draw the alpha cleavages? I did. Did I draw the McLaffertys? I did. And then did I draw radical cations on the spectrum? I did, with arrows pointing at their signals. Yes. Did I label an isotope peak? I did. And a representative for it? I did. That's the representative. I could do other isotope peaks if I wanted to. Like I can do the isotope peak of this one right here. I can have a carbon 13 on the thing, or this one's got an isotope peak right there. This one also isotope peak right there. There's all kinds of them, right? I had a question. What do I mean by representative? Oh, representative. So this isotope peak right here, it could be because a carbon 13 occurs at that carbon, or it could be this carbon or this carbon or this carbon or this carbon or this carbon. I don't have to draw all of them, just one representing all of them, one representative. And we're not done yet. I mean, this is a long quiz. I didn't realize. Okay, so this next one, I'm asking you to use a rule of 13 to calculate a molecular formula for the molecule with the following mass spectrum. Label the molecular ion and 3 isotope peaks. Okay. So we're just looking for a molecular formula. So the first thing I notice is this double looking thing. What does that suggest, that doublet? With the left side a little taller and the right side a little shorter? Bromine. Exactly. And then let's figure out what this is too. I'm gonna have to zoom in on this. That's 50. 1, 2, 3, 4, 5. Yeah, 55 is a little longer. So it's 56. 156 there. And then this one is 158, huh? Yeah, so that looks like bromine. So I'm going to take my formula, my molecular ion. By the way, which one is the molecular ion? Is it the 156 or the 158? It's the 156. The 156 because that has the most abundant isotope of bromine, the bromine 79. It's only slightly more abundant, but that's the definition of a molecular ion. Most abundant isotopes, bromine 79 is most abundant. I'm going to subtract the 79 right at the start. I like to do the calculation that way. So I get 7 here, 14 there, 77. So I've taken out the bromine. Let me double check that. 79 and 77 better still add up to 156. This is 6, 150. Yep, that's good. And now I'm going to do rule of 13 on the 77. And let me do it. I'll cheat with my calculator a bit quicker. 13. It's going to be 5 with the remainder 1, 5, 5, 65. It's 2 and 1. Remainder of 12. It's got a big remainder, huh? Does that work out mathematically? 12 times 5 is 60. 72. Yeah, looks good. Or no, 60. Did I do that right? 77. 12 times 5, 55, 60 plus 12 is 72. Something's wrong. Let's do 77 divided by 5. No. 77 divided by 13. Okay, minus 5 times 13. But yeah, I'm doing it wrong. It's 13 times 5 when I double check. My double check was the error. It's 6. Yeah, 77. There we go. Sorry. When you do your double checks, make sure you do them correctly too. Okay, so I got it. So this looks good. It's going to be a C5H. There's 12 plus 5, 17. And then I got to remember to add in that bromine. 5 and 12, 7. Let's make sure that adds up to 156. Let's make sure we got this right. So it's 60 plus 17 plus 79. Yep, 156. Looking good. So does this seem reasonable? Let's look at our degrees of unsaturation. It's going to be 5 plus 1 minus 17 plus 1 halogen minus 0 nitrogens all over 2. It's going to be 6 minus 18 over 2. 6 minus 9 minus 3 degrees unsaturation. It's not looking good. That's way too many hydrogens, huh? Not enough carbons. Okay. So let's fix this. Let's use, let's try the one we haven't tried yet. Let's see, a carbon 12 equals 12. 12 hydrogen ones, right? So let's see. We want to get rid of some hydrogens, so I'm going to use that. I'm going to go C5H17Br. I'm going to add a carbon. Well, actually, I'll write it up more the way I usually do it. No, I guess I got to do that. Plus a carbon minus H12, 12 hydrogens. So now I'm C6H5Br. Okay, that looks like it's going to work. That's going to be more reasonable. So what does this still add up to 156? It has to, unless or I made a mistake. So 6 times 12 is 72 plus the 5 plus the 79, 156. This looks pretty good. I think this is good. So use a rule of 13 to calculate a molecular formula. Okay, I got it. Label the molecular ion and 3 isotopes. Okay, there we go. So that one works. But Well, I'm pretty sure it does, but let's just make sure. 6 plus 1 minus 5 plus 1 minus 0 all over 2. 7 minus 6 over 2. 7 minus 3, 4 degrees of unsaturation. I think that works. I can drop something like that. If it's got 6 carbons. Oh yeah, this is really easy. I bet this is the actual molecule. Because you got 6 carbons and you got 4 degrees of unsaturation. Benzene gives you 4 degrees of unsaturation. It's got 1, 2, 3 bonds, 1 ring. And then if I throw my bromine on there, do I have 5 hydrogens? Yeah. I bet you this is the actual molecule's mass spectrum. So that works. And now let's label 3 isotope peaks and the molecular ion. Let's do it. So the molecular ion, that's easy. It's just the radical cation with a 79 on it. Bromine. That's that one, right? Another one we can label is bromine 79 still. But one of the carbons, say that one's a carbon 13. That would be this guy, huh? An isotope peak. And then we can draw some of the bromine 81 isotope peaks. So if I have bromine 81 right here, then that's going to be this one. And finally, I could do one more. It only asks for, actually it asks for 3. I asked for 3 isotope peaks. I gotta do one more, huh? So I got bromine 81 again, but maybe like a carbon 13 there. That will be this little guy. And I could have added an oxygen to the formula. I see some of you are asking about that. Yeah, we could have tried to draw up another one, but this one works. I didn't actually have to draw a molecule here either. I could have just said, that's the molecular ion. I'll show you what I mean by that. I could have just said, okay, this is my molecular ion right there. And then I have my molecular ion plus 1 for like a carbon 13. That's down, way down in there, right? That's getting ugly, but you know what I'm saying. And then this one is your molecular ion plus 2 due to the bromine 81, etc. Okay, so this is taking longer than I wanted, but I'm glad I went through a lot of examples for you. And I do want to do one last thing before we quit on this. So you have the key to the quiz, but I also wanted to do, or at least start, I'll just kind of do it quickly here, a multiple spectrum problem that involves not giving you the molecular formula. Instead, it gives you the mass spec only. So I'll start this problem out and I'll get you to the point where you can do it. So on this problem, I'll give you an example. I'll give you a problem like this on the exam too. You'll get one of these. You have to look at this thing and figure out the molecular ion. This looks like the molecular ion right there. Where is that at? That's at 70, 71, 72, 73, 74. That's 74. So it's not odd. It looks like no nitrogens, right? It's not a doublet, and it's not 79 plus, so, or doublet. So that means no bromine. But I do see right here, I have an alcohol, huh? So it has an oxygen, which equals CH4, remember? So let's do it. Rule of 13 on '74. So Ashley asked, how did I know that one was the molecular ion? I don't 100% know, but it sure looks like it. There's a little isotope peak afterwards. And on the exams, when it's not obvious, I'll tell you. I pretty much always just tell you. I'll put it on an exam question. I just put a box usually right here saying the molecular ion is this, because a lot of times it's not super obvious. Good question. So 74 divided by 13. I get 5 again. 1, 5, 65 again. Yep. This is 9. And then, do we already have this already? I think we did, huh? Wait. 74 divided by 13. 5 times 13. Remainder of 9. Yep. So I double checked that. That looks good. So it's looking like C5H14. When I double check the mass of that, it's 5560, 74 again. Yep. And I know I need an oxygen, so I'll subtract CH4, add oxygen, C4H10O. This looks good. I have 1, 2, 3 carbon signals for 4 carbons. I think that can happen because you have symmetry for the molecule. And also I see this proton NMR signal, this big doublet. That looks like an isopropyl group to me. And if I have 10 hydrogens and I decided to go like 1 hydrogen for this integration, 1 for this one, how many would this integration curve be if those other ones are 1? Be 2 hydrogens, yep. And if that's 2 hydrogens, does this look like the rest? So I have 10, that's 2, 3, 4. Does this look like 6 hydrogens? Yeah, I could see that being 6 hydrogens. I think this formula looks good. 4 carbons, 10 hydrogens. Yeah, and I'm feeling like an isopropyl group here because I need to have like a 6 hydrogen doublet here. And so right away, that already takes care of 1, 2, 3, 4 carbons. So now it's just, where do I put the alcohol? Do I put the alcohol here? Or do I put the alcohol here? This one would have a 2 hydrogen doublet. And this one would have, oh, this would actually be a 9 hydrogen singlet. So it's not that one. Yeah, I got to erase this. This was my earlier work. Adding the alcohol there is not going to work, huh? I want to demonstrate, though, when you just start drawing out possible molecules, you can figure it out. Where this one has the 6 hydrogen doublet, looking good. 1 hydrogen, no. So that one looks like the answer. Yep. We got it. Pretty cool. Now you can do multiple spectrum problems without that like crutch of having to be given the molecular formula. Just all spectra, you can do it. Okay, we didn't start chapter 8, which means the final will not have as much chapter 8. I'll let you know on soon about that, what's going to be from chapter 8. It'll be, I'm going to pick things from chapter 8, which are basically from chapter 7. they're going to be like how to make an alcohol. Yeah, so it won't be crazy. It won't be the whole 15 outcomes from chapter 8.